Okay, let's do a quick demo of the Rslk running Ros. So, before we get going, what are we looking at here? This is a TI Rslk. I have a custom hat attached to the top of it. On that hat, there is an XB, which is communicating with my desktop wirelessly. No wires. And attached also to the hat is a servo, which is going back here. There's a gear on the end of the servo, which is connected to a linear rail, which attaches to this pen, which is a custom mount that allows us to lift and lower a pen. And just because I know the camera isn't the best, here are some visuals. This is what the board looks like unpopulated. This is populated. We have the ability to hook up LiDAR, other servos, all kinds of stuff. This is the connection between the XB and the computer. This was the first pen plotter. This is the one that's currently on there. And this is a demo of kind of what is going on there. Okay, so time for the actual demo. So what can you do with controlling the Rslk via Ros? So we're listing out a few of the things that we could do. So bumpers. The Rslk is publishing the bumper status. There are 6 bumpers on the front. It is subscribed to the command velocity, which allows us to control the motors as well as that servo. It is publishing the motor status, which we'll get into, and it also using TF we are able to see where the robot is in relation to the origin point in space. So if you wanted to test the bumpers, you could we're going to echo back the bumper signal to us. So we have an array of 6 elements here. Left to right, 0 means bumper is not pressed, 1 means bumper is pressed. So, again, going left to right, and you can have multiple bumpers pressed at the same time, no problem. What else can we do? We can also listen to where it is in space, right? So this is not going to be super fascinating, but basically we are at the origin point. Probably tapped the wheel when I moved it a little bit, so that's why it's not exactly at 0, 0. If you wanted to move that servo, for example, you could do a Ros topic publish. So again, it's on a command velocity, it's twist message. So the servo is connected to our linear Z because Z. So 1 will lift that pen. Good. So you can see that. You can see any other stuff. So 1 will lift that pen. Nice. And then we can just as easily lower the pen. So that's that. Now if you wanted to monitor what's going on with the motors, you can do that as well. Which I'm gonna shrink this back down to where it was. Kind of. Right there. Okay, so if you wanted to monitor what's going on with the motors, you would motor status. Now what motor status is an array of 6 elements again. This time the left 3 are for the left motor, right 3 are for the right motor. The first element is a 1 or -1, which means either forward or backward. The second element is the PWM of that motor, going from a range of 0 to 255. And the third element is the current wheel speed forward in meters per second. So again, not rotation speed, but actual how fast it's moving the robot forward in meters per second. So if you wanted to, so if you were to move this forward, you can see that we're moving here, and you can also see the left speed here. So that's what's going on with that. And if you wanted to watch that in real time on something easier to see, let's see, you could open up the simulation, which would be Ros topic, no, Ros launch. Ros launch Rslk world.launch. And now we are opening this. We have simulated version of our robot right here. So if I was to, and X is forward, so if I was to, we're now moving forward, as you can see. So there's chassis encoder, and then there's chassis simulation. So simulation is actually what has been sent to it, and encoder is what has been read by the encoder. So we have yet to send any movement data to this, therefore the simulation thinks it's still at 0, 0 because it hasn't received any command messages, while the encoders know it is no longer at 0, 0. This is helpful for if there's wheel slippage or something like that, or if, you know, the wheel happens to bump into something and it moves slightly. Now this will be more accurate to where it is in real space versus that. But having them both published at the same time gives you a dead reckoning kind of visualization to, if you were to tell it to go somewhere and it did hit something, and every time you give it a new movement, the error will keep accumulating. This kind of shows that error accumulation over time. So if we wanted to tell it to drive forward at 0.1 meters per second, these are both, remember I had turned this one. So this, again, this is perfect. This is the actual one. And you can see the simulation, that's the simulated image of it. So if I was to now slow down this motor, you can see how that happened. Now, it autocorrected. Why did it autocorrect? There's a PI controller controlling the speed of the motor. So again, it's supposed to go 0.1, it's currently going 0.93, 0.95, 0.93, 0.95. Both of motors are moving forward, and PWM of 26 for each motor. Now if I'm to slow down, let's put it back here. If I'm to slow down this motor, you see how it's slowing down, but the PWM jumped up, overcorrected a little bit, and so by the time it overcorrects and then recorrects, it almost puts it back on course. Not quite. So yeah, there's that. And again, you know, that works for both motors. So you see we're jumping up 50, 52, 53. Nice. Okay. I think that's about everything I wanted to show. So yeah, that's it. Thank you.